Oh, it says, hello, everyone. Good morning, good afternoon, good evening, depending on when you're watching this. Just a reminder that if you have any questions during the talk, please feel free to post them into the chat, and I'll try to interrupt the speaker perhaps and post them. But it's my pleasure to introduce Professor Hanany, who will be giving his section lecture in his series today. Please take it away.
Thank you very much. Yeah, let me start. Let me first share the screen. I will my first slide is going to be a reminder of the exercise from yesterday. So I hope people manage to compute the Hasse diagram for the Higgs bunch of SU409 flavors by two methods. First, bottom up using the Higgs mechanism, and second, going top down using the method of Quivers subtraction. So if you find it too hard, then we should go over the algorithm again. Please share whether you managed or not.
Maybe as we're thinking about that, would you mind full screening your slides, please?
Sorry, yes, thank you very much.
Thank you.
Yeah. Now, next example that I would like to discuss is the case of G2 gauge group with n hypermultiplets transforming in fundamental representation. This is just a hyperkähler quotient. However, the gauge group is exceptional, and as a result, we are not aware of Coulomb branch construction for the corresponding modular space. So we only use the hyperkähler quotient construction for this space. And I'd like to point several interesting features of this modular space. So that's quite a challenge to derive such a diagram. But let's go over the details. So first of all, we see that there are 4 leaves. In the physics language, these are 4 phases of different master states. There are 3 slices which separate between them of type C at the bottom, A and D. And recall that those notations, so when I write lowercase d, I mean the minimal nilpotent orbit for the algebra of D type with this index, with this rank. And similarly, when I write A, it's the minimal nilpotent orbit, or the closure of the minimal nilpotent orbit of A type. And Cn is something new we haven't seen before. That's the closure of the minimal nilpotent orbit of SPN. It's actually an orbifold. It's just a Z2 quotient of C2n, where the action of Z2 is on all coordinates reflecting the signs. Okay, now several things to learn from this is that first of all, from one diagram with 4 leaves, I can construct as many as 6 symplectic singularities. So we would count them 1, 2, 3, 4, 5, and 6. Right? So this is one nice feature that in a single Hasse diagram contains many symplectic singularities. The biggest one is the one that we see over here, and this is the quiver for it, a G2 gauge group with n copies of the fundamental representation. Because the fundamental representation of G2 is real, the global symmetry is of type SP. Any questions so far? But please free to stop me at any point. Okay, and so now using the Higgs mechanism, what we can do is to go to this step over here, this gauge over here, by finding that SU3 is a subgroup of G2. We make the procedure that Keeble devised, we follow it, and we find that this is the number of flavors. We did an example. I hope this example is sufficient to do all of the other examples. But if not, please ask. We could do several other examples. It's just an exercise in the compositions of irreducible representations from one group to a subgroup. Okay, and then for SU3 with this number of flavors, the Hasse diagram is already known. We computed one example in the previous lecture. We found that it is of type A and D. The only thing which changes is we need to fit the labels here with the number of flavors here. And we did the case SU3 with 6 flavors, but it is straightforward to generalize it to any number of flavors. Okay. One interesting thing to look at is this slice here. The gauge group is SU3. It is embedded inside G2, and we can ask what is the subgroup that commutes. What is the commutant of SU3 inside G2? And this is a maximal subgroup. So it turns out that there is a discrete subgroup which commutes. It's denoted here as O1, as Z2. And that's the group which acts on Cn to give us this particular slice. So that's an interesting point. Another thing is that the commutant of SU2 inside G2 is SO3. Here's the quiver. This slice is not an nilpotent orbit. It's a Z2 cover of a nilpotent orbit. So that's a fun fact. If it was O3 instead of SO3, then it would be a nilpotent orbit of Cn. So, and I think those are my comments for this Hasse diagram.
Yes. Quick question. So the big singularity on the right, so the full, is that the closure of a nilpotent orbit as well, or?
Oh no, not at all. Not at all.
No.
It's so this structure here, DAC, does not show as a sequence in a Hasse diagram of any nilpotent orbit.
I see.
But already, yeah. I mean, it could be so. I believe the case with the n equals to 2 might be. So there would be special cases. So generically, it's not. There might be special cases for low number of flavors where it is. If I'll have to compute it, but if I remember correctly, for so G2 with two flavors shows up in a 6-dimensional embedding of string theory. It's one of those cases which are anomaly free and appears on, if you know the language, it appears on a -3 curve in F theory. And well, there is a trivial case. If you set n equals to 1, you only have C1, those have negative labels, so it's just one-dimensional, and then for sure, this is an nilpotent orbit, right? So it's, but once you add this guy, this one is not a nilpotent orbit.
But the fact that at each step we are seeing a minimal nilpotent orbit, is that part of the theorem of Kraft-Pachesi, or?
Yes, right. So there is a set, that's a very interesting mathematical question. There is a set of minimal transfer slices, and I think it's not settled. What is the classification of all such transfer slices? In the case of Kraft and Pachesi, they worked only on nilpotent orbits of classical type. And they showed that the only slices are of type A and D for the Klein singularities, and the minimal orbits of classical type for otherwise, and that's it. Right? There's nothing else. In fact, Alex is here, and so he, in his paper, they found several new slices. So if you look at the Balasubramanian for G2 and for C, because towards the bottom of the Hanany diagram, there's no room for stretching simple roots. So you have to go in slightly downwards way, and there you'll find new slices. So this is nice. It actually goes back to work by Stembridge, I believe. Maybe Alex has an earlier reference, but I think it shows up in the work of Stembridge.
I think that's right. I was just going to comment that there's a theorem of Daniel Juteau that those slices that you get really are distinct up to isomorphism. So yeah, just one comment.
I see. Thank you. Thank you. I didn't know that. Okay. It's good to have Alex with us. Any more questions? Okay, and the next example of Hanany diagram, it's probably the last one. Here we see that this is a Hanany diagram, maybe for the first time in this set of lectures, that we see a bifurcation in the Hanany diagram. If you come from top down, you see it over here. If you come from bottom up, you see the bifurcation here. So physically, this bifurcation happens because I have two matter fields, two types of representations. One is in the antisymmetric and the other is in fundamental. And this typically would give two different global symmetries, and global symmetries of the symplectic singularity will typically show up at the bottom. There's two, so I have 12 fundamental hypermultiplets. The global symmetry is SU12, so I see it over here. And one antisymmetric of SU4 happens to be a real representation, and therefore the global symmetry is SP1, and you see it over here. So now in terms of the Higgs mechanism, I can go bottom up. And from this point, at this point, SU4 is, that's the origin. SU4 is unbroken. If I go along this, what we call flat direction, then this is the theory that we have. So SU3 is unbroken. If I go along this way, the theory that we have is this one, and SP2 is unbroken. So you could work your way up with the Higgs mechanism, do the compositions, and then you find that the common subgroup of SU3 and SP2 is SU2, and you're done, right? So that's going bottom up. We do have a quiver. I don't have it in this slide, but in the paper it is there. There is a quiver such that the Coulomb branch is this modular space. And so you could use this Coulomb branch and the method of quiver subtraction to work your way downwards and fully consistent. So this is a good test of the procedure for quiver subtraction, because we do not have a proof for this technique. It's just it's based on a set of observations. Any questions? Okay, so the next point that I will cover is the monopole formula. I'm leaving the topic of magnetic quiver for the last lecture, where I will show different ways of computing magnetic quivers. So the monopole formula appeared in the list of characterizations that we can do on a symplectic singularity. We went over the dimension, the global symmetry, the phase diagram or the Hasse diagram, and now we are ready to compute the Hilbert series for symplectic singularity, and we will focus on the Hilbert series for the Coulomb branch. There is a Weil integration formula for the Higgs branch, which is based on the hyperkähler quotient, but I will not go over here unless there will be some request to do that. Okay, so let's first of all put the ingredients which need to enter into the monopole formula. First of all, I put, so I have a quiver with nodes and edges that connect them, and I assign a group. I use here the complexified version, but you could also think about the UK gauge group. That's the more gauge theoretic way that we do in formulating the problem. But I think all of the groups below would be complexified. So, so you have a node of label K, you assign this group, it has a Weil group, symmetric group of order K, and then there is a corresponding dual lattice. So physically, it's the lattice of magnetic charges. So those are the magnetic charges. We label them M1 up to MK. And now we can act on them with the Weil group. So there's going to be a principal Weil chamber which orders those magnetic charges. We also need to deal with boundaries of the Weil chamber, and those happen whenever some of those values M are equal. And as a result, the subgroup that commutes with the fixed such set of charges would vary depending on on which boundaries I'm in. If all charges are equal, then the subgroup that commutes is the full UK. But if all of them are non-equal, then the subgroup which commutes is B1 to the K, right? So there is a set of Levy subgroups of UK which will be needed in all of the cases over all of the boundaries. We'll have to sum over all contributions, and the contributions will change depending on the value of HM. Any question?
Yeah. What M is a vector of integers. So what do you mean by its stabilizer in a continuous Lie group?
Just look at the subgroup that rotates them. I don't know if this is the right way of saying it. What I mean is that I'm going to collect a set of equal numbers, and then for this set, if I have J of them, then the subgroup will be UJ, and then the next set will have another UJ, and so on. Right? So it really, in terms of one other way of thinking about this is that those magnetic charges are background charges for masses of BPS states, and so when some of them are equal, I get a corresponding massless state, and the corresponding gauge boson will be now part of a non-abelian symmetry, rather than the case where all of them are different, and then the group will be U1 to the n. So if you don't like the way I call it, just think about this set of integers and divide them into cases where some of them are equal and in groups. So the number of such cases HM will correspond to the number of partitions of K.
Yeah, I mean, sure, you can just say I have a partition and that picks out the Levy subgroup. And I mean,
yes, right. So
that's fine. I just, I wouldn't have thought of GLK as acting on the lattice lambda hat. That was my only.
I see. Well, I'm not the person to be on the right language. I may fail in the.
You should go on.
Maybe I can interject one thought. I think you can think of M as determining a one-parameter subgroup of GLK, and then it's really the centralizer of that subgroup. I don't know if that's helpful.
Okay, Jacques?
I'm happy either way.
Okay. Oh, and then one last point. Yeah. So given HM, I need to take the set of Casimir invariants, and in particular, I need the degrees, which are denoted by DIM. And I think I have an example in the next. Yeah. If I have GL2, the value group is S2. I start with a set of unordered integers, the magnetic charges. I order them using the Weil group. The boundary happens when they are equal. And now I have two cases to consider, equal and different, where I have U1 squared versus U2. Okay, and the degrees would be, for the first case, 1 and 1. but for the second case, it's going to be 1 and 2. Okay, so those are the ingredients which are needed in order to put into the Monopole formula. Any questions? Okay, so now let's also go over the gauge group and remind that there are two essential cases: quivers without flavor nodes and quiver with flavor nodes. So the gauge group will be UK. The label of the nodes is given by A. And then since there is no flavor node, I have to divide by an overview 1, which acts trivially on all matter fields. And then once I have this gauge group, there will be a dual lattice and a while group. So it will be just the product of those lattices and the product of the while group. Okay, the next thing to consider is in case that the quiver has a flavor node, then I don't need to divide by an overall U1. The gauge group is just the product of all UK and yeah, that's it. So this is a simple point. Please stop me in case you have any question. And here are some examples of the freedom that I have in case that there are, well, I can either go from right to left or from left to right. So if I start with a quiver that has no gauge nodes, I can pick any of the nodes, ungauge it, and then I get this quiver with flavor nodes, and there is an equivalence. The Coulomb branch of the left guy is the Coulomb branch of the right guy. In addition, also the Higgs branch of both sides is the same. Right? So this is a graph equivalence. Here's another example where I have an edge of multiplicity 2. It's still simply laced, and then another edge. If I ungauge over here, I get this graph equivalence. And here's another example. Okay. It's important to remember this because if I don't ungauge, I may encounter infinities in the computation of the Hilbert series. And here is another example. I could also engage on a node which has rank higher than 1. Then the corresponding group is SU2 rather than U2, also over here. Right? So all of those quivers are equivalent. Okay, the next point is to consider the conformal dimension, delta of M. This is also the highest weight of the, or at least half the highest weight of the corresponding, we call it monopole operator under SU2R. So we think of the monopole operator as a holomorphic function. It has a degree, and delta of M will be half this degree. So we need to define delta of M. When we say C star grading on a Coulomb branch, what we mean by this is that we take SU2R, we take the U1 subgroup of SU2R, and we give a holomorphic function weight under this U1, and that would be encoded by delta. So delta will get contributions from both nodes and edges according to the following prescription. So actually, to make this computation, this is a computation which was first done by Kapustin and his students back in early 2000. And they used a technique of computing the Casimir energy in the background of a magnetic charge, fixed magnetic charge. But we won't go over the details of that computation. We will just state it that if I have a node which has magnetic charges Mi with label A for the node, then I will get a negative contribution, which looks like this. Okay. So conceptually, each such contribution corresponds to a positive root of the algebra. For each edge that connects two different nodes A and B, the first one has magnetic charges MIA, the second MJB. We will put a positive contribution, which takes this form, 1/2 times the difference in absolute value. And this is associated with the fundamental representation, bifundamental representation under the two gauge loops that it connects. Okay, so what we're going to do for delta is to collect all of the contributions from all nodes and all edges. So it will give me some long formula, and I'm going to use it. And now we will have the monopole formula, which is this one. Right? So I need to sum over all magnetic charges in the lattice, take a variable t and raise it to the power twice delta, and multiply by we call this a dressing factor, and this dressing factor uses the information we had for the Levy subgroups. So for given magnetic charge M, I will have a corresponding Levy subgroup HM. This subgroup will have a set of Casimir invariants, and they will show up over here, and I will need to take the product of all such Casimir invariants. Okay, any questions for the definition of the Hilbert series? That's the monopole formula. Now I should say some words about this monopole formula. This really was a breakthrough in understanding, at least for me, it was a breakthrough in understanding three-dimensional N=4 Coulomb branches, because with such a formula, we were able to compute systematically many properties of many modular spaces. We just managed to do it. So you teach the computer how to do it. It's fairly easy, and then you could evaluate many quivers. So this really helped in identifying many modular spaces. One other crucial thing was that it was this formula that I showed to Nakajima back in 2014. And that was the thing which convinced him to start working on this topic. And now it's a big topic in representation theory. So sometimes the details are important for conceptual development. Very good.
Quick question.
Yes.
Are we again making this assumption like the theory is good or something like that in writing this monopole formula?
Oh, very, very nice question. So indeed, because, let me go back, because delta can have, it has both positive and negative contributions here. It may be negative, and in this case, the Hilbert series may have convergence issues. So I'm always taking the strict viewpoint that I only deal with the quivers where the only solution for delta equals 0 is where all of m's are 0, right? And delta is always non-negative. Right? So there's only one case where delta is 0, and for all other cases, delta is positive. And this would be good for conical moduli spaces. If you fail to be conical, then you'll probably have problems with the value of delta for some choices of n. Okay.
Okay, thanks.
Yeah, so it's just that, so it's really as simple as that. The techniques we have are only good for cases where delta is non-negative. They will fail for other cases, and then we'll just have to come up with different techniques. Okay, so one simple example, which is like straightforward exercise, is to take the case of a linear quiver. So it's an A-type quiver of finite type. So you'll have n+1 gauge nodes, each with the label 1, so it's U1 to the n+1, and then connected by n edges. And since all nodes are gauge, I have to remember to ungauge one of them. So I'll get a moduli space of dimension n, a Coulomb branch of dimension n. And it would be nothing special, just Hn. So if you'd like to do the exercise, you could check that when you plug the prescription into the Monopole formula, you get the Coulomb branch for Hn, which takes this form, 1 over 1 minus t to the 2n. And it has this expansion. That's the complex dimension of the moduli space. And this is the dimension of the global symmetry, which acts on Hn, SPn. Any questions? Okay, so let's learn to read some numbers out of the Hilbert series. Oh, but before that, I have some set of examples. So this is a set of examples from the cases of simple nilpotent orbits of A-type. The quivers are here. We have the quaternionic dimension in this column. And this is the labeling of the nilpotent orbit as a partition. They are all of SL type. So you just add the numbers and you figure out which SL it is. Now, over here, this is SL2. So the nilpotent orbit of SL2 has this Hilbert series. This column is what we call the generating function for highest weights. So the way to read it is to take an expansion. If I expand in powers of t, I will find that at order t squared, there is a contribution of mu squared. And what I need to do is to replace any monomial in mu with the character of the corresponding powers. So at t squared, I will have the character of the representation with dignity label 2. So that's the adjoint. And so I'll get the contribution of 3 weights over there. At order t to the 4th, I'll get mu to the 4th. So I'll get character of the representation with dignity label 4. So it's 5-dimensional and so on. So the expansion of this in Taylor series gives me the information about all representations. And there are conversion formulas from the formal variable mu into explicit characters of the corresponding algebra. And so this is a very nice way of encoding the information. You see that it is slightly simpler than this expression. This is an unrefined expression. And this expression really contains all of the representation content of the holomorphic functions on this moduli space. So you see how simple they become, quite complicated functions, and there is this expression. Any questions about the concept of a high-squared generating function? One interesting comment to make is that most moduli spaces will have this expression to be very complicated. In this table, we collected cases where the high-squared generating function is just a simple product of rational factors. One way of saying it is that if I take the statistic exponential of those monomials, I would get that the high-squared generating function is a PE of a polynomial rather than an infinite series. And so we could consider the class of moduli spaces for which the high-squared generating function is a PE of a polynomial. Those are particularly simple moduli spaces. They belong to some class, possibly multiplicity-free varieties, or sometimes I heard the name spherical varieties. It would be interesting to try and formulate some conjecture for such moduli spaces, because there are very few which behave like that. Most spaces are really having very complicated expansion. Okay, so this is something to think about. In fact, in our work, when we try and compute moduli spaces, we give special attentions for moduli spaces where the high-squared generating function is a simple function. Questions?
So you're saying it's still unclear what the sort of geometric property is that renders this high-squared generating function simple? Is that the...
So the closest I saw are those two concepts of, if you're familiar with multiplicity-free varieties. So a multiplicity-free variety is a variety where for given representation, there is at most one holomorphic function in this representation. For given, if I have multiplicity two holomorphic functions of the same representation, that's not multiplicity-free. No multiplicities, either 0 or 1.
I see.
So this one is of this type, this one is of this type. There are few cases where you could see that this notion, and there are some papers, math papers, which expand on notion of multiplicity-free varieties. They don't necessarily restrict to symplectic singularities. It could be Gorenstein. It could be even more general than that. So there is some studies of this type. Another concept where I don't know the precise definition, maybe Alex can say something, is the class of varieties which are called spherical varieties, and they are similar in the behavior, but perhaps there is some precise definition. I also saw the name wonderful varieties. So yeah, I mean, it would be nice to study those guys and see whether there is a connection or not.
Thanks.
Okay, so yeah, if you have any comments, questions, please let me know. In fact, one more comment I could say is that when we do orbifolds and we want to compute Hilbert series, many times it's easier to act on this function and to get exact expression rather than to use the monopole formula. Sometimes the monopole formula is too long for a computer to compute, and on the other hand, when you have exact expressions like that, you could work out very nice orbifolds for those. Okay, now let's go back to more immediate things. So I can read the complex dimension of the Coulomb branch by evaluating the order of the pole of the unrefined Hilbert series at t equals 1. So for this, I need to know the exact rational function of the Hilbert series, or alternatively, I saw some techniques that use Pandit approximations in order to evaluate the complex dimension. So if you want to get this information from the Hilbert series, that's a doable thing. Next, we discuss the global symmetry. So we want to see how it is realized in the Hilbert series. So if I expand, if I write the Hilbert series as an infinite sum with coefficients Cn, Cn's are dimensions of reducible representations of the global symmetry. C2 takes a special form. Remember, yesterday we said that the functions of degree 2 transform in the adjoint representation of the global symmetry. So in the Hilbert series, this is this function, the coefficients of t squared. So this necessarily is in the adjoint representation. Sometimes you could find mistakes in your computation if it doesn't fit into an adjoint representation. Now, if C1 is non-zero, then it's necessarily even. That's because we are dealing with a symplectic singularity. So in fact, if C1 is non-zero, it indicates that there is a factor of h to some power. So what I can do is to write a new Hilbert series, which takes the C1 out by multiplying. And this is a Hilbert series for a different Coulomb branch. And the Coulomb branch I started with will be the new one times a power of h, which is precisely C1 over 2. Okay. Any questions about this one? So sometimes there would be quivers where you would compute values of C1 which are different than 0, and then you just factorize the modular space into two components, trivial and the non-trivial. Questions? Okay, the notion of balance we discussed yesterday. The only thing I wanted to show is that there is some nice formula for this. If you take the vector of gauge nodes and label them by K, the vector of flavor nodes labeled by F, and the Cartan matrix by C, then there is a vector expression for the balance. And if I demand that all nodes are balanced, there is actually a nice exercise to do and to convince yourself that the simply laced guys would be of type affine ADE. You could also add the non-simply laced edges, and then you'll find the classification of all affine and twisted affine algebras. That's it. Those are the only cases where the nodes are, all nodes in the quiver are balanced. Any question? Okay, next we can introduce a refinement. For each node, I can introduce a function, which is a linear function on all magnetic charges. So I just sum over all magnetic charges for a given node of label A. And then I introduce a variable, fugacity ZA, and refine the Hilbert series by adding this factor here. And if I compute the refined Hilbert series, I can again write it as a power series in T, and Cn now will be characters of representations of the global symmetry, whereas C2 will be the character for the adjoint representation. Okay. Okay. So now I'm done with describing the Hilbert series. So in principle, if you follow the prescription that we gave in these slides, you are now able to compute properties of many Coulomb branches. As many as you wish, you could teach a computer to do that, and you have a window to many modular spaces, many Coulomb branches. The next point that I would like to discuss is to emphasize the process of quiver subtraction. So I'll stop here in case you have any questions about the Hilbert series. Okay, so if not, let's just discuss the work of some of the aspects of the work of Graf and Procesi. They told us that the minimal transitions between neighboring leaves would be of two types, either a Klein singularity of type AD actually, and or a closure of minimal nilpotent orbit of some algebra, the classical algebras. That's from, so the work of Graf and Procesi were only on classical algebras, but you could try and extend it to the exceptional, and then you'll get this one, and you'll also get the nilpotent orbit of exceptional type, except that the list is bigger. There are many other singularities. There is a paper by 4 people Fu, Jutor, Somers, and Paul Levy, which really gives a very detailed account of all Hasse diagrams, including minimal degenerations for the exceptional cases. Okay, so let's just recall the Hasse diagrams for the nilpotent cones, the first few cases. So you see that they are linear up to SL5, and then we get some bifurcations, and it becomes more and more complicated as we proceed. And what I would like to do is to take one of them, I think it's going to be this one, and go over the process of quiver subtraction and to show how I can reproduce the whole diagram by applying the technique of the quiver subtraction. Any questions? So these are these are the quivers that I'm going to need. Right? There is the AN, capital AN. The Coulomb branch is the Klein singularity of type A. So C2 mod Z n plus 1. And the lowercase a, AN, this is the minimal nilpotent orbit of SL n plus 1. Its closure. So what's the algorithm? Let's recall. We said it yesterday, but let's just clarify. I take a quiver, I identify subquivers, which are in the list of minimal singularities. I align those quivers for the minimal singularities and subtract from the quiver that I have. Some of the nodes are going to lose the balance that they had before. So I'm going to rebalance. I'm going to add flavors to all of those nodes which changed balance in such a way that I insist that under the subtraction, the balance is fixed. I get a smaller quiver, so I can apply the algorithm again and then proceed until I stop. Okay? So Aswin, you were unclear. Maybe that's the time for asking questions.
I'll maybe wait till you go further and ask.
Very good. Okay, so now,
sorry if I may interrupt for a second. I was just noting the time, but maybe after this topic will be a good time to stop.
Yeah, if you, I could rush the thing. We should finish, right?
Should finish sometime, I guess, but this seems like an interesting topic too. So.
Okay.
There have been quite a number of questions. Usually we run for an hour and 5 or something like that. So, yeah, okay. I mean, yeah.
Okay, so I can go over this example and then we will stop there. Okay, so let's take the nilpotent cone of SL6. It's given by the Coulomb branch of this precise quiver. And what I want to do is to compute the Hasse diagram. So I look at all possible subdiagrams that I can fit into this, and there's only one. And that's the diagram, which is U1 with 6 flavors. Right? So I'm going to align it below here. The corresponding slice is the slice A5, capital A5. So let me remind, we had this, it's this one, right? So A5 is 1 with 6. So I subtract, 5 minus 1 gives me 4. And these guys are, they are balanced. So 1 is balanced, 2 is balanced, 3 is balanced. They don't lose their balance. On the other hand, 4 is changing its balance. And so in order to keep the balance, it was balanced before. Now the label here is 4, so I need to remember that in order to balance it, I'll put a flavor 1 here. And in order to balance this 4, I need 4 over here. Okay. So I end up with this quiver. The claim is that the Coulomb branch of this quiver is the subregular, the closure of the subregular orbit of SL6. And one can actually test it by either computing explicitly or using other techniques. Any questions?
So in the first step of the subtraction, only the gauge nodes are involved, or are you also subtracting like 5 from the 6? Are the flavor nodes also involved?
So I need to look for a subdiagram which fits into this structure of 1 and n, or a fine algebra.
Oh, okay, sorry. So in the first step, all of the flavors went away, but then you sort of added 4 back for the balance condition.
For the balance, that's right.
Ah, I see, okay.
You could, I mean, there's also a brain picture for this subtraction. And in the brain picture, you could see that 4 out of 6 of the brains, of the flavor brains, are just spectators. They don't take part. Where the other 2, they move to the sides. One moves to the left, the other moves to the right. Moving to the right gives you the flavor over here, and moving to the left is just going away from the picture. Any questions? Okay, so then the next step. Now I have this quiver. I cannot fit over here a singularity because the moduli space for U1 with 1 flavor is just H. It's not a singularity. On the other hand, here I can fit U1 with 4 flavors. So I subtract an H3 and I do the same procedure. So 4 minus 1 is 3 and all others remain the same. And I rebalance again. So I get this quiver. Okay. Now I get an interesting situation. The next quiver will have 2 ways to subtract, either from here or from here. So I get the bifurcation. So there are 2 ways to subtract. Let's do the first one. If I subtract from here, I'm left with 2, all the others stay the same. And rebalance, so it gives me this quiver. On the other hand, if I have the subtraction here, I subtract over this, so the 4 becomes a 3. The rest are untouched, but rebalance gives me these flavors. Okay? Now, if you remember the Hasse diagram for the nilpotent cone of SL6 had the bifurcation precisely at this point. Next, what I can do is to perform the subtraction. I have to work on both of those quivers. So let's start with this one. So here I see that I can subtract U1 with 3 flavors. It will give me this quiver. Right, so all other nodes are the same. The 4 becomes a 3, and the rest is determined by rebalancing. In fact, this rebalance is just, you could also think of it as reducing 2 from the node, and those 2 show up on the neighboring nodes. And so 3 becomes a 1, and then each one adds 1. The same thing happens here. So if so again, I identify Na2, so U1 with 3 flavors, I subtract it. This becomes a 2, and the others are untouched. So I get this quiver again. Notice that I converge to the same quiver. And then from the flavors, I subtract 2 over here, becomes 1, and then the neighboring node gets one flavor here, but there is no node here, so it goes away. Any questions? Okay, so now I see that there is another bifurcation I can take, and this time we find 2 ways, 2 embeddings of the minimal A2 orbit. So here's the quiver, 1, 1, 1, and 1, which I subtract. If I do that, then the 2 becomes a 1, the 3 becomes a 2, and rebalancing gives me 1 flavor over this, and the rest are untouched. On the other hand, I can subtract this A2. If I do that, then this the node 2 remains the same. 3 and 3 becomes 2 and 2. Then these are untouched. The rebalance gives me 1 flavor here and 2 flavors here. So you see, again, I have bifurcation, but this time by subtracting an A2 in 2 different ways. Okay. We proceed. We are almost done. So next case, I have an A1 from here, A1 from here, doing the subtraction. I get this quiver. And now I should identify that this is a minimal, sorry, it's not yet a minimal. So there's one more step. Now I recognize that there is an A3 over here. Right, so there is an A3 subdiagram. So I should subtract it. I subtract the A3, I get this one. And now this is an A5. I subtract this one and I'm done. Okay, so let's collect all of the cases. There we go. Okay. Very neatly reproducing the procedure that Kraft and Pachesi did. I'm done.
Oh, well, let's thank Professor Hanany for a great talk.
Thank you.
Any more, perhaps quick questions? I know we did stop with a lot. So.
So I hope after this detailed exposition, we know how to subtract many families of moduli spaces. It would be interesting from a mathematical point of view. It would be interesting to prove such procedures.
I think that presentation is very clarifying at the end. Oh, I'm sorry. Please go ahead.
No, yeah, I was going to say that's really fascinating. So this is now known for. So the fact that this subtraction procedure works is known for all type A nilpotent orbits, or what's the?
Yeah, this is very clear, very easy for type A. You know, life is good with type A, and so it's quite straightforward. You could show that any orbit is derived. More interesting is for cases where you go beyond nilpotent orbit. So you could ask whether there are in the affine Grassmannians. So, and for the affine Grassmannian of finite type, let's say A, So there are very nice theorems in the paper of Alex and his collaborators. So for example, they show that most transitions in the affine Riemannians are of type capital A, so Klein singularity of type A. And very few, if you consider compared to all, very few are different than Klein singularity of type A. So that's one interesting point. Yeah.
Sorry. Yeah. If you're finishing a thought, I had a question, but I can do.
Go ahead. Yes.
No. So, like from the point of view of, okay. Let me see if I get this right. So, in all of these quivers, which one is the nilpotent orbit? Is it the Higgs branch or the Coulomb branch?
Always the Coulomb branch.
Always the Coulomb branch in these cases. Okay. So then there is the following kind of question one can ask. So if we have some conical symplectic space which arises as the Coulomb branch of some quiver gauge theory, are all of its symplectic leaves also describable by as Coulomb branches of quiver gauge theories? That's the kind of thing you're showing, right? So the step-by-step procedure sort of explicitly constructs an answer to this question, but is there a general answer known?
There would be some difficult cases. One thing which comes to mind is the quiver for the subregular orbit of G2. So you know that the nilpotent orbit below it is not even normal. So then I don't know a quiver for this guy, and I also don't know how to subtract. So the quiver for subregular G2 contains an adjoint. So I don't know what to do in such cases. I don't know how to do subtraction when adjoint matter is involved. I could do several observations, but it doesn't look too useful. So, so maybe what you're saying would be to a class of well-behaved quivers. So if I don't have loops, and if I just consider quivers of finite type with framing, then those seem to be well-behaved, and they will be covered by the procedure of quiver subtraction.
Interesting.
So those would include the nilpotent orbits and slices in the affine Riemann.
Perhaps that's a good place to officially stop then. I mean, we can continue a little, but thank you very much again for a great talk.